Section: Introduction. In this section, we delve into the concept of learning from teachers, LFT, and machine learning, particularly in the domain of large language models, LLMs. LFT involves methods like knowledge distillation and distillation via synthetic data, which focus on transferring knowledge from teacher LLMs to student LLMs through token logits, features, and synthetic data. These techniques are crucial for bridging the performance gap between different types of LLMs and for maintaining performance during model compression. Moreover, teaching not only benefits students but also enhances the teachers themselves, a concept known as learning by teaching, LBT, or the Feynman method of learning. This approach aids in building more robust and clear knowledge. We aim to explore whether LLMs can also learn through teaching, potentially offering new avenues for model improvement by teaching other models rather than solely relying on human-generated data or stronger teacher models. To investigate this idea, we break down LBT in human learning into 3 levels: observing students' feedback, learning from the feedback, and iteratively learning from the feedback. We aim to apply these LBT principles to LLMs and study their feasibility through 3 methods corresponding to the 3 LBT levels. Our initial exploration involves methods to enhance LLM's answer quality and inherent ability by leveraging students' feedback. By scoring and optimizing teacher-generated rationales based on their teaching effectiveness, we demonstrate improvements in answer accuracy and model performance. Additionally, we highlight the potential of LBT and LLMs to enhance weak to strong generalization and benefit from diverse student inputs. In essence, with the right frameworks and teacher-student dynamics, LBT shows promise in enhancing LLM's capabilities. These early investigations only scratch the surface of LBT's potential in advancing LLMs, suggesting that integrating advanced educational techniques could further optimize LLM training and performance. Section Summary. In this section, we delve into the concept of learning by teaching, LBT, in the context of large language models, LLMs. We explore how LBT methods, inspired by human learning processes, can be applied to LLMs to enhance their answer quality and inherent capabilities. By leveraging feedback from students, in this case, other models, LBT shows promise in improving LLM performance and potentially unlocking new avenues for advancing these models through iterative teaching strategies. Section: Improving the answer quality without training. In this section, we explore different ways to enhance the quality of answers without the need for training. We have looked into various aspects of human reasoning that have been used in prompting-based methods, such as explaining the thinking process, breaking down subproblems, extracting abstract principles, refining answers through self-reflection, and more. We have investigated 2 methods that incorporate the learn by teaching, LBT, insight. The first method, M1, is linked to the well-known search-based output generation pipeline. This method involves sampling and evaluating new rationales or rationale steps iteratively to find the best output. A crucial component here is the evaluator, which assesses the quality of each rationale based on its effectiveness in teaching student models to solve similar problems. The second method, M3, is related to existing prompt optimization techniques that enhance prompts based on their performance metrics like accuracy and failure cases. What sets M3 apart is its evaluation approach. Instead of using the same model that generated the prompts, M3 tests how the prompts work with other student models, leading to better prompt tuning outcomes. To enhance the inherent capability of the model, method M2 incorporates the LBT insight into the generating scoring fine-tuning pipeline. This method involves 3 steps: generating multiple rationales for a given problem, scoring these rationales using an evaluator, and using the scores to train a verifier and fine-tune the model through various techniques like reinforcement learning and supervised fine-tuning. Unlike traditional methods that rely on manual labeling or ground truth matching for scoring rationales, M2 evaluates rationales based on their ability to teach student models to solve similar problems, enabling automatic and detailed quality assessment. Additionally, we introduce a scoring method based on LBT principles, where the quality of a partial rationale is evaluated based on how well another, completer, model can arrive at the correct answer by continuing from the partial rationale. This method emphasizes examining students on similar problems using the teaching problem and full rationale as examples. In method M1, for LBT Level 1, we adopt a common teaching strategy where a teacher provides a teaching rationale and answer for a specific problem and then tests students on similar problems to gauge their understanding. We implement this strategy in language learning models, LLMs, to select high-quality teaching rationale answer pairs. By instructing the teacher model to solve a given problem multiple times and using the resulting pairs to guide student models in solving similar problems, we can assess the quality of the pairs based on the student's performance. The final teaching answer is selected based on the highest LBT score or by aggregating scores for exact matching problems like mathematical reasoning. Section Summary. In this section, we explore methods to enhance answer quality without training by incorporating insights from human reasoning processes into prompting-based techniques. We investigate two approaches. One involves implementing an evaluator based on the learn by teaching (LBT) insight to score generated rationales, while the other focuses on optimizing prompts by evaluating their performance with various student models. These methods aim to improve answer quality by leveraging the ability of rationales to teach student models effectively. Section: Experimental Setups. In this section, we utilized the math dataset extension and split the problems into training and testing sets. Among the 500 test problems, 181 had 3 different versions each. We selected these 181 problems as our target problems, TPs. For each TP, we created 256 pairs of teacher rationale, TR, and student answer, TA. These TR-TA pairs were used as examples for iterative concept learning, ICL, with the 3 versions of the TP serving as example problems, EPS. Each learning session was repeated 3 times with random decoding by students, resulting in 9 pairs of expected rationale, and expected answer, EA. The student's performance was evaluated based on the correctness of these 9 EAs. Our results are presented in a table and further analyzed. We found that our method, referred to as M1, outperformed baseline models significantly across various settings. M1 showed effectiveness in scenarios like strong teach weak, weak teach strong, and self-teaching. Additionally, we observed that M1, sum, generally performed better than M1, max. By using GPT 3.5 to teach multiple concepts simultaneously, such as Llama 3-8B and Mistral 7B, we achieved notable improvements compared to teaching each concept separately. M1 demonstrated the ability to identify correct answers even in rare cases. Furthermore, we showed that the similarity between target problems and example problems is crucial for effective learning. In another experimental setup using the Grandmaster Dynamic Programming Study Plan on LeetCode, we evaluated the correctness of Python code solutions. Each problem had visible test cases, and we assigned scores based on the code's performance on these cases. We then assessed the code's correctness on hidden test cases to obtain a more comprehensive evaluation. Our results indicated that M1 outperformed agreement-based methods like self-consistency in most cases. We also found that the quality of the teacher rationale and student answer pair significantly influenced the student's performance on example problems. Moreover, we explored the impact of self-debugging on code quality assessment. By applying self-debugging techniques, we were able to improve the correctness of student answers, complementing the evaluation done by M1. Overall, our method showed consistent improvements, especially for problems of medium difficulty. We also observed that having the teacher and student from the same model family led to more informative feedback and better learning outcomes. Section Summary. In this section, we utilize the math dataset extension with various problem variants for training and testing. We focus on 181 test problems with 3 functional variants each, sampling TR-TA pairs and using them as exemplars. By repeating exams with randomized student decoding, we evaluate the effectiveness of our approach in surpassing baselines significantly across different model settings. Additionally, we emphasize the importance of selecting EPs similar to TPs to enhance student learning and problem-solving abilities. Section: Method. In this section, we explored how we can enhance student performance by improving teaching materials based on the feedback received. By using the LBT-based scoring system, we collected scores for many TR top pairs to refine the teacher with DPO. We conducted experiments using 1564 training problems from math as TPs. Each TP had 32 TR top pairs, and we calculated a score for each pair based on correctness and LBT score. We then used DPO by selecting pairs with score differences above 0.3 and keeping a maximum of 8 pairs for each TP. Our results indicated that using LBT scores in DPO led to better outcomes compared to solely relying on correctness scores. LBT provided more insightful scores, which helped in distinguishing between TR top pairs effectively. We further investigated the iterative improvement process by having multiple LLMs act as teachers and students. By learning from diverse feedback, the teacher could create more effective teaching materials. This iterative process involved using positive and negative exemplars based on student performance with ICL examples. We evaluated this method, named M3, on 2 text classification tasks, liar and logical fallacy. The results showed that applying LBT on iterative prompt optimization was beneficial, leading to performance gains. Having dedicated students, different from the teacher, improved the quality of teaching materials faster, showcasing weak to strong generalization. Overall, our approach demonstrated the potential of leveraging LBT for enhancing teaching material quality through iterative improvements with multiple LLMs playing different roles. Section Summary. In this section, we explore how student performance can guide the improvement of teaching materials in education. By iteratively refining teaching strategies based on student feedback, we aim to enhance the capabilities of language models, LLMs. Through experiments, we demonstrate that leveraging LBT scores in iterative prompt optimization can lead to significant improvements in the quality of teaching materials, especially when multiple LLMs with distinct roles of teacher and student are involved. Section: Limitations and Near-Term Extensions. In this section, we explore the limitations and potential extensions of the LBT-based scoring in models M1 and M2. This scoring method helps in selecting high-quality TR top pairs but requires that the TP and EPs have similar problem-solving strategies. In our experiments, we choose suitable EPs based on human-provided information in the dataset. One extension we consider is having a model automatically identify EPs similar to a TP from a large pool. Another direction is to create similar problems by synthesizing them based on a group of problems and predefined mutation strategies. For instance, as an extension to M2, we can generate a new problem P by using a group of known similar problems S equals P_1, L dots, P_k. We then apply the generating scoring pipeline to P to get rationale score pairs, where the LBT score is calculated using S as the EPs. However, one limitation of LBT-based scoring is the additional cost of LLM inference. Although this cost is lower than human annotation for M2, further improvements are needed to reduce it, such as enhancing the method or using efficient inference systems. Building upon the framework presented in the introduction and related work sections, we can explore various ways to incorporate LBT insights into the inference and training pipelines of LLMs. For example, to enhance the quality of answers for a TP, we can integrate the concept of having the teacher review feedback from multiple students into the output generation pipeline. This process involves the teacher iteratively reflecting on each student's feedback and updating the TR accordingly. The final answer is then determined by combining the updated TR from each student. Encouraging diversity in TR generation can improve the accuracy of aggregation methods. Moving on to the concept of weak to strong generalization, the traditional approach involves improving models using human-generated annotations or synthetic data from stronger models. However, we consider a new perspective on continuously enhancing the strongest model without relying solely on human-generated data. By leveraging weak model supervision to train a larger model, we can still enhance the performance of large models to some extent, as shown in recent studies. Furthermore, we delve into the idea of borrowing design strategies from teaching materials. We present an LBT pipeline that includes steps such as the teacher generating teaching materials, students learning from them, providing feedback, and the teacher reflecting on and updating the materials. By continuously updating teaching materials, both the teacher's knowledge and the student's learning experience can be improved. Additionally, we can draw insights from educational pipelines to design inference and training pipelines for LLMs. For example, task-oriented collaborative learning where multiple LLM agents collaborate to learn a challenging topic, and progressive learning where a junior model teaches a stronger student, can be beneficial strategies to explore. These approaches can help in continuously improving LLMs by leveraging educational principles. Section Summary. In this section, we explore the limitations and near-term extensions of the LBT-based scoring approach in selecting high-quality TR top pairs, highlighting the need for TP and EPs with similar problem-solving strategies. One extension involves automatically identifying EPs similar to a TP and synthesizing similar problems based on predefined mutation strategies. Additionally, we investigate the concept of weak to strong generalization by using weak model supervision to train larger models, aiming to continuously improve superhuman models without relying solely on human-generated data. Section: Acknowledgement. In this section, we express our gratitude for the support received from various funding sources, including the National Natural Science Foundation of China, Tsinghua EE Xilinx AI Research Fund, and Beijing National Research Center for Information Science and Technology. We also acknowledge the support from Infinigence I. Additionally, ZW and MBB received support from the Research Foundation, Flanders, FWO, and funding from the Flemish government under the Onderzoeksprogramma Artificiële Intelligentie, AI, Vlaanderen program. We are thankful to LumiB for granting access to the Lumi supercomputer and to the Euro HPC Ju for providing access to the Leonardo supercomputer. Special thanks to Zixuan Zhou, Chao Yu, and Boxen Li for their valuable discussions. Regarding author contributions, the specific roles of each equally contributing author are outlined as follows. Shifei Ning, Project Leader, Idea Generation, Story Development, Field Survey, Method and Experiment Design for M1, M2, and M3, Implementation and Oracle Experiments for M1, Preparation of Method Figures. Zifu Wang, Experiment Design, Implementation, and Execution for M1 Math and M2. Xiao Li, Experiment Design, Implementation, and Execution for M1 Code, Preparation of Method Figures. Zinan Lin, Project Leader, Story Development, Method and Experiment Design for M1 and M3, Oracle Experiments for M1. Peiran Yao, Method and Experiment Design, Implementation, and Execution for M3. Furthermore, all authors contributed to the analysis of experimental results and the writing of relevant sections. Shifei and Zinan took the lead in the analysis and writing process.